this lab, we investigated electric circuits and capacitor behavior using real physical circuit components, including batteries, resistors, ammeters, a voltmeter, and a capacitor. The purpose of this lab was to compare predictions from an ideal circuit model with measurements from a real circuit. We applied several fundamental physics principles, including Ohm's law, Kirchner's loop rule, and the RC time constant model. Our main result was that the experimental data closely followed the theoretical predictions, but small differences occurred due to internal resistance in real component and measurement limitations. To model the circuit, we used several fundamental physics principles. First, Ohm's law, which states that the voltage is equal to current times resistance. This allows us to predict the current flowing through a circuit when the voltage and resistance are known. Second, we use Kirchhoff's loop rule, which states that the total potential change around a closed loop must equal zero. In other words, the voltage provided by the battery must equal the total voltage drops across the circuit components. Finally, we use the RC circuit model, which describes how capacitors charge and discharge over time. The time scale of this process is given by the time constant, T, which equals resistance multiplied by capacitance. The system we studied was a series electric circuit consisting of 2 batteries and 2 resistors. The batteries provided a total voltage of 3 volts, and the resistors had a value of 47 ohms and 100 ohms. The surrounding environment includes the wires and measurement devices that connect the circuit. In the RC experiment, the capacitor was initially uncharged before connected to the circuit. Using our theoretical model, we predicted the current through the circuit. Since the resistors are connected in series, the total resistance is the sum of the 2 resistance, which is 147 ohms. Using Ohm's law, we divided the voltage of 3 volts by the total resistance to obtain a predicted current of 0.0204 amps, or about 20.4 milliamps. Next, we measured the current and potential differences in the circuit. The measured current values were approximately 15.7 milliamps, which is slightly lower than the predicted value. We also measured voltage drops across each component using a voltmeter. These include the 47 ohm resistor and 100 ohm resistor and the ammeter. To test Kirchhoff's loop rule, we added all the potential differences across the circuit. The total came out to approximately 0.027 volts, which is very close to zero. This small difference occurs due to measurement uncertainty and internal resistance in the circuit components. This result supports the prediction that the total potential change around a closed loop should equal zero. Next, we studied the behavior of a capacitor in an RC circuit. When the capacitor begins charging, the current is initially large, so the bulb appears bright. As the capacitor stores charge, the current decreases, causing the bulb to gradually dim. We measured the charging and discharging times using 2 resistors. The larger resistance produced a longer charging time, which agrees with the RC time constant model. Our observations match the RC circuit model. The time constant is equal to the resistance multiplied by capacitance. This means increasing resistance increases the time required for the capacitor to charge and discharge. Our experimental results confirm this prediction, since the circuit with the large resistance took longer time to charge and discharge. There are several sources of error that explain the small differences between our model and the measurements. Real batteries have internal resistance, wires add additional resistance, and measuring devices such as ammeters introduce small voltage drops. These factors cause the measured current to be slightly lower than the ideal theoretical prediction. Now consider a scenario where a capacitor is connected directly to a battery with no resistor. In the ideal model, the time constant T equals RC. If the resistance is 0, the time constant becomes 0, which predicts that the capacitor would charge instantly. However, this does not occur in real circuits. All circuits contain some resistance from the battery, wires, and measurement devices. Because of this, the capacitor charges very quickly but not instantaneously. In conclusion, our experiment demonstrated that real circuits generally follow the predictions of ideal circuit models. Our measurements confirmed Ohm's law, loop rule, and the RC charging behavior of capacitors. Small differences between the model and the experimental data occurred due to internal resistance and measurement limitations in real circuit components. Thank you.